Welcome to White Space. What actually happens when temperature has no limit? Put this on in the background. Close your eyes if you want, and let the story carry you. Let's begin. There is a moment just before sleep when the mind drifts beyond familiar things, when the noise of daily life dissolves and something older, quieter, and far larger takes its place. That feeling of standing at the edge of something incomprehensible is what the universe produces in anyone willing to look at it honestly, because the universe does not offer comfort. It offers scale, and scale, when truly understood, changes everything. We measure our world in degrees. In the warmth of a fire, in the cold of winter, in the fever of illness. These measurements feel real to us because they are drawn from experience. But experience, it turns out, is an extraordinarily narrow window. The range of temperatures that life can tolerate spans perhaps a few hundred degrees. The range that exists in the universe stretches across more than 40 orders of magnitude. What lies at the extremes of that range is not merely hot or cold. It is a different state of reality altogether. Begin with cold. The coldest place in our solar system is not some distant moon locked in shadow. It is a crater near the south pole of the moon, a small bowl-shaped depression that has never in billions of years seen a single ray of sunlight. Inside it, the temperature sits around minus 240 degrees Celsius, close to absolute zero. Close to the point at which matter itself surrenders its restlessness and becomes almost completely still. But even this is not the true minimum, absolute zero. Minus 273 degrees Celsius is the temperature at which all thermal motion ceases. No vibration, no rotation, no kinetic energy of any kind. It is a theoretical limit, unreachable in practice because reaching it would require the removal of all energy from a system, and the universe does not permit that. Even in the deepest vacuum between galaxies, a faint thermal radiation persists, the echo of the Big Bang, now cooled to just 2.7 degrees above absolute zero. Everywhere you go in the observable universe, that background whisper is present. The universe has not forgotten where it came from. And where it came from was hot, incomprehensibly violently hot, in the first fraction of the first second after the beginning. The temperature of the universe was so extreme that the very concepts we use to describe heat become insufficient. Modern physics gives this limit a name, the Planck temperature. It is approximately 142 nonillion degrees, a number that requires 32 digits to write. At that temperature, the fundamental forces of nature were unified. Gravity, electromagnetism, the strong and weak nuclear forces, all merged into a single undifferentiated fury. What happened at or beyond that temperature is not something current physics can describe. The equations break down, the map ends, and beyond the edge of the map, we simply do not know. This is perhaps the most honest sentence in all of science. We do not know. As the universe expanded and cooled, structure began to emerge. The quarks that had floated freely in an impossibly dense plasma began to bind together into protons and neutrons. Protons and neutrons assembled into atomic nuclei. Electrons joined them. The first atoms formed, mostly hydrogen, some helium, traces of lithium, and from those three elements, everything that followed was eventually built, every star, every planet, every molecule in every living cell. All of it descended from the cooling of that original fire. The journey from the Planck temperature to the present required only about 14 billion years. Which sounds like a long time until you consider that the period during which atoms first formed lasted only a few 100,000 years. Out of that total, the early universe was a story told at extraordinary speed, with the most dramatic events compressed into the opening moments. What we observe today, galaxies, stars, the pale blue light of an inhabited world, is the slow aftermath. But the aftermath still contains extremes that beggar imagination. Take Venus. The second planet from the Sun is, in many ways, the great cautionary tale of planetary science. It is almost the same size as Earth, almost the same mass, almost the same distance from the Sun. Early astronomers speculated that it might be a world of tropical forests and shallow seas, perpetually shrouded in cloud. The reality when spacecraft finally penetrated that cloud layer in the second half of the 20th century was profoundly different. The surface of Venus is hot enough to melt lead. The average temperature there is around 465 degrees Celsius, higher than the surface of Mercury, despite Mercury being far closer to the Sun. The reason is the atmosphere, a crushing blanket of carbon dioxide 90 times denser than Earth's air, trapping heat with ruthless efficiency. A runaway greenhouse effect taken to its logical conclusion. Venus is what happens when a planet loses control of its own climate, and the result is a world that is, by every measure we value, completely dead. Yet even Venus is cool compared to what lies deeper in the solar system's catalogue of extremes. The innermost moon of Jupiter, Io, is the most volcanically active body in the solar system. Its surface is painted in sulfur yellows and oranges, constantly reshaped by eruptions that never stop. The heat driving this activity is not the decay of radioactive elements, as on Earth, but tidal friction. Jupiter's enormous gravity squeezes and stretches Io as it orbits, and that mechanical stress generates heat in quantities sufficient to keep the interior perpetually molten. Temperatures inside Io's volcanic vents exceed those found on the surface of the Sun's photosphere. A moon no larger than our own has temperatures at its surface exceeding 1500 degrees Celsius in places and far higher beneath. The Sun itself, seen from a sufficient distance, looks deceptively mild, a yellow star, medium-sized, unremarkable by galactic standards. But the numbers attached to it are not mild. The core of the Sun maintains a temperature of roughly 15 million degrees Celsius. The pressure and density there are sufficient to sustain the nuclear fusion reactions that have been burning for nearly 5 billion years. Hydrogen nuclei, stripped of their electrons, collide with enough force to fuse into helium, releasing energy in the process. Every second, the Sun converts 600 million tons of hydrogen into helium and releases energy equivalent to billions of nuclear weapons. It has been doing this continuously since before Earth existed. It will continue for approximately another 5 billion years. The surface of the Sun, the visible layer we call the photosphere, is around 5,500 degrees Celsius, surprisingly modest compared to the core. But moving outward from the surface, something strange occurs. The temperature, rather than continuing to fall with distance, suddenly increases. The solar corona, the ghostly halo visible during total eclipses, reaches temperatures of 1 to 3 million degrees Celsius, far hotter than the surface below it. This paradox has puzzled solar physicists for decades. Why should a region farther from the energy source be hotter? The explanation likely involves the churning of magnetic field lines at the solar surface, generating waves that carry energy outward into the corona and deposit it there as heat. But the details remain an active area of research. The Sun, the most studied star in the universe, still holds secrets. During solar flares, explosive releases of magnetic energy from the surface, temperatures in the erupting plasma can reach tens of millions of degrees. For a few minutes, a relatively small region of the solar atmosphere becomes hotter than much of the solar interior. These events hurl charged particles into space at a significant fraction of the speed of light, creating waves of plasma that, when they reach Earth, can disrupt satellite communications, damage power grids, and produce auroras visible far from the poles. The Sun, in these moments, is not the benign provider of warmth and light we tend to imagine. It is a machine of extraordinary violence, periodically reminding its neighbors that it is also a nuclear weapon of planetary scale. But the Sun is ordinary. By galactic standards, it is so ordinary as to be nearly unremarkable. Red dwarf stars, dimmer and cooler than the Sun, outnumber all other stellar types by a considerable margin. Their surface temperatures hover between 2000 and 4000 degrees Celsius. They burn their hydrogen so slowly and carefully that some will still be shining trillions of years from now, long after the universe has grown cold around them. At the other end of the spectrum, the hottest normal stars burn blue-white, with surface temperatures exceeding 30,000 degrees. They consume their fuel at a rate so profligate that their lifetimes are measured in millions of years rather than billions. Bright but brief, spectacular but unsustainable. And then there are the wolf-rayet stars. These are not normal stars in any sense. They are, in most current understanding, the exposed cores of massive stars that have shed their outer layers through the force of their own radiation, stellar winds so powerful that they blow off entire shells of gas over time scales of hundreds of thousands of years. What remains is the bare nuclear furnace, blazing at temperatures that can exceed 200,000 degrees at the surface. Some wolf-rayet stars are even hotter. They are extraordinarily rare, extraordinarily bright, and extraordinarily short-lived. In the entire Milky Way galaxy, fewer than a few hundred have been catalogued. Each one is a countdown, a star burning itself to nothing at maximum intensity. The most extreme stellar remnants push even further. When a massive star exhausts its nuclear fuel and collapses, the outer layers rebound in a supernova explosion of almost incomprehensible energy, briefly outshining entire galaxies. The core left behind is compressed to densities at which normal matter cannot exist. Protons and electrons merge into neutrons. The result is a neutron star, an object with the mass of the Sun compressed into a sphere perhaps 20 kilometers across. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth. At the moment of formation, the surface of a neutron star reaches temperatures near 100 billion degrees Celsius. Even as it cools over millions of years, it remains one of the hottest objects in the universe. Its radiation streams out primarily as X-rays, invisible to the naked eye but detectable by orbiting observatories, which have catalogued thousands of these objects scattered across the galaxy like cooling embers from ancient fires. And yet, neutron stars are not the end of the sequence. When the most massive stars collapse, the remnant core exceeds even the ability of neutron degeneracy pressure to resist gravity. The collapse continues, the density increases without apparent limit. Space itself curves so severely around the object that nothing, not light, not information, nothing can escape from within a certain radius. A black hole forms the boundary of that region of no return. The event horizon is not a physical surface, but a mathematical boundary, a point of no return in the geometry of space-time. What lies within is, by definition, unobservable from outside. The temperature attributed to the space just outside a black hole, not the object itself, which has no conventional temperature, can, in the case of actively accreting black holes surrounded by infalling matter, reach extraordinary values. The innermost regions of quasar accretion disks have effective temperatures estimated at tens of trillions of degrees. These are the hottest persistent environments currently observed in the universe. At the centers of active galaxies, supermassive black holes with masses millions or billions of times that of the Sun drive the most energetic phenomena we have ever recorded. Jets of plasma accelerated to near the speed of light, reaching lengths of millions of light years, powered ultimately by the conversion of gravitational energy into radiation. The universe, it seems, has found numerous ways to generate extreme heat. and it has found equally inventive ways to put on a show. Among the most beautiful shows the universe offers is the solar eclipse from the surface of Earth. At this particular moment in geological time, we are extraordinarily lucky. The moon's apparent diameter in our sky is almost exactly equal to the apparent diameter of the Sun. The moon is about 400 times smaller than the Sun. But it is also about 400 times closer, and these two factors cancel with remarkable precision. The result is that during a total solar eclipse, the moon's disk can cover the Sun almost exactly, revealing the ghostly streamers of the corona in the darkened sky. Stars become visible in the middle of the day, birds fall silent, temperatures drop. For a few minutes, the geometry of the solar system produces one of the most arresting experiences available to a human being. This coincidence will not last. The moon is very slowly drifting away from Earth, about 3 to 4 centimeters per year due to tidal interactions. In roughly 600 million years, the moon will be too far away to completely cover the Sun, and total solar eclipses will no longer be possible. What we will have instead are annular eclipses, in which a ring of sunlight remains visible around the moon's disk. Beautiful in their own right, but lacking the total darkness and the visible corona of the total eclipse. Future civilizations, if they exist, will know that their ancestors once witnessed a phenomenon they themselves cannot. Eclipses are not unique to Earth. Anywhere in the solar system where a moon is large enough and well positioned enough, some version of this phenomenon occurs. On Mars, the two tiny moons, Phobos and Deimos, are too small to cover the Sun completely, but they pass across its disk frequently, creating partial transits that have been photographed by Mars rovers. In the outer solar system, the giant planets and their large moons create eclipse geometries of their own. Jupiter, with its dozens of moons, experiences constant shadow play. Moons casting shadows onto Jupiter's cloud tops. Moons entering Jupiter's own enormous shadow, one moon occasionally eclipsing another. The system is never static. It is always in motion, always producing new configurations of light and shadow. For planets orbiting other stars, eclipses, or more precisely transits, have become one of the most powerful tools in the search for worlds beyond our solar system. When a planet passes in front of its star from our perspective, the star's light dims by a tiny but measurable amount. By timing these dips and measuring their depth, astronomers can determine the planet's orbital period, its distance from its star, and its size relative to the star. The Kepler Space Telescope, operating for nearly a decade, monitored over 150,000 stars simultaneously, looking for these minute fluctuations. It found thousands of planets. Many of them orbit in the habitable zones of their stars, the region where liquid water could theoretically exist on the surface. Some of them are rocky, roughly Earth-sized. The question of whether any of them host life is one of the most significant open questions in science. We do not know, but we now know that planets are extraordinarily common. The galaxy is full of them. Some of the most extraordinary transit events discovered involve not planets, but dust clouds, planet-forming disks, and the debris left by disintegrating worlds. In a few rare cases, astronomers have observed stars that dim irregularly and by large amounts, sometimes losing 15 or 20% of their light over a period of months or years, in patterns that no simple planetary explanation can account for. These systems hint at processes of planetary formation and destruction that we are only beginning to understand. Rings of debris thousands of times larger than Saturn's rings, clouds of gas and dust migrating through complex gravitational interactions, the wreckage of worlds that once existed and no longer do. The universe builds and it destroys often simultaneously. Nowhere is this more apparent than in the life cycle of stars. A star begins as a cloud of gas and dust, slowly collapsing under its own gravity. As the cloud contracts, it heats. When the temperature at the center reaches about 10 million degrees, nuclear fusion ignites and the star is born. The pressure of outgoing radiation balances the inward pull of gravity, and the star settles into a state of equilibrium that can last millions or billions of years, depending on its mass. More massive stars burn hotter and faster. Less massive stars burn cooler and slower. This is not a metaphor. It is literally how it works. Mass determines fate. A star with less than about 8 solar masses will end its life relatively gently. As it runs low on hydrogen in its core, it expands into a red giant, eventually shedding its outer layers as a beautiful glowing cloud called a planetary nebula. What remains is a white dwarf, a small, dense object, no larger than Earth, slowly cooling over billions of years. White dwarfs are extraordinarily common in the galaxy. They are the final state of the vast majority of stars that have ever existed, including the eventual fate of our own sun. But sometimes in binary star systems, white dwarfs get a second chance. If a white dwarf is orbiting a companion star, and the two are close enough, the white dwarf can draw material from its companion, through gravitational attraction accumulating a growing layer of hydrogen on its surface. This stolen hydrogen eventually reaches the conditions necessary for nuclear fusion and ignites in a sudden explosive flash, a nova, that can briefly increase the white dwarf's luminosity by a factor of thousands. When the conditions are right and the accumulated material exceeds a critical mass threshold, the entire white dwarf can detonate in a more violent event, a type Ia supernova. This explosion is so predictable in its energy output that astronomers use type Ia supernovae as standard candles to measure distances across the universe. It was through observations of these events that astronomers first discovered, in the late 1990s, that the expansion of the universe is accelerating, driven by what we now call dark energy, a force whose nature remains completely unknown. The most massive stars live differently. They exhaust their hydrogen quickly, then begin fusing heavier elements, helium, then carbon, then neon, oxygen, silicon. Each successive fuel burns faster and generates less energy. The star's interior develops an onion-like structure of nested shells, each burning a different element surrounding an iron core that grows steadily heavier. Iron is the end of the road for nuclear fusion. Fusing iron requires energy rather than releasing it. When the iron core reaches the Chandrasekhar mass limit, the point at which electron degeneracy pressure can no longer support it, it collapses in a fraction of a second. The outer layers, falling inward and rebounding, produce the most energetic explosion in the observable universe, a core collapse supernova. In that explosion, more energy is released in a few seconds than the sun will radiate over its entire 10 billion year lifetime. Most of that energy, over 90%, is carried away by neutrinos, ghostly particles that pass through entire planets as easily as light passes through glass. The remnant of this explosion is a neutron star, or if the collapsing core was massive enough, a black hole. The outer layers, scattered into space at significant fractions of the speed of light, form an expanding nebula of hot gas that will glow for thousands of years. Inside that nebula, the compact remnant continues to radiate, spin, and in some cases, pull in more material. The Crab Nebula, the remains of a supernova observed and recorded by Chinese and Arab astronomers in the year 1054, is still expanding today, driven by the energy of the pulsar at its center, a neutron star spinning 30 times per second. The elements created in stellar interiors and scattered by supernova explosions are not wasted. They seed the interstellar medium with the raw materials for future stars and planets. Carbon, oxygen, nitrogen, iron, calcium. All of the elements heavier than hydrogen and helium were forged inside stars and distributed by their deaths. Every atom of iron in your blood was created in the core of a star that died billions of years ago. Every atom of calcium in your bones came from a supernova explosion. You are, in the most literal sense, made of stardust. The poetic observation has a rigorous scientific foundation. In the most extreme stellar collisions, elements heavier than iron are created. Iron is the peak of energy efficiency in nuclear fusion, but neutron star mergers can produce neutron-rich conditions so extreme that nuclei can capture neutrons faster than they can decay. This rapid neutron capture process, the R process, builds up the periodic table beyond iron all the way to uranium and beyond gold, platinum, uranium. The heaviest elements in the universe were made not in peaceful stellar interiors, but in the violent merger of neutron stars. The gravitational wave event detected in August 2017, the first observation of merging neutron stars through both gravitational waves and electromagnetic radiation, produced a kilonova, an explosion creating a cloud of newly forged heavy elements, including an estimated mass of gold equivalent to tens of Earth masses. In that single event, more gold was created than exists in the entire solar system. The universe is occasionally prodigiously generous with its raw materials. Among the most extraordinary individual stars in the galaxy, one class deserves particular attention. The blue supergiants, massive, hot, and luminous, are among the most visually impressive objects in the night sky. They are not the most common type of star. In fact, they are extraordinarily rare. But their intrinsic brightness means that they are visible at enormous distances, and some of them can be observed with the naked eye despite being thousands of light years away. Their surface temperatures typically exceed 25,000 degrees Celsius. Their luminosities can be hundreds of thousands of times greater than the sun's, and they live fast and die young. A blue supergiant may spend only a few million years on the main sequence before the forces at work in its interior drive it toward a more volatile evolutionary path. What makes blue supergiants particularly interesting to astronomers is their instability. Their radiation pressure is so intense that it constantly threatens to overwhelm gravity and blow off the outer layers of the star. The stellar winds they generate, streams of particles blowing outward from the surface, can reach velocities of 2,000 kilometers per second. The mass loss rates are enormous. Over its lifetime, a blue supergiant may lose a significant fraction of its initial mass simply by blowing it away. The material dispersed in these winds forms beautiful structures in space, shells of gas and dust, glowing under the ultraviolet radiation of the star, visible as nebulae in long exposure images. They are, in a very literal sense, a star unmaking itself. Some blue supergiants are also runaway stars, objects moving through space at velocities far higher than their neighbors. These stars were likely launched from their birthplace by a supernova explosion in a binary system. When the companion star exploded, the gravitational bond between the two was severed instantaneously. The surviving star, released from orbit, continued moving at whatever velocity it had at the moment of separation, shooting away from the explosion site like a stone released from a sling. These stars carry their origin stories in their trajectories by tracing their paths backward. Astronomers can sometimes identify the nebula that marks the site of the explosion that set them free. The eventual fate of a blue supergiant is one of the most dramatic events the universe produces. As the star exhausts its core hydrogen and evolves away from the main sequence, it moves through a sequence of phases: yellow, supergiant, luminous, blue, variable, perhaps a Wolf-Rayet phase, stripping away layer after layer. At the end of this sequence, if the remaining core is massive enough, a supernova explosion occurs, leaving behind either a neutron star or a black hole, wrapped in the expanding remnant of the explosion. If the star passes through a red supergiant phase first, the supernova will explode into a dense circumstellar medium, producing a brilliant display as the ejector slams into the previously shed material. When we think about the largest stars in the universe, a different kind of wonder emerges. Size, in stellar terms, is not the same as mass or luminosity. The most massive stars are not the largest in physical extent. The most luminous stars are not the largest in radius. The truly enormous stars, the red supergiants and hypergiants that occupy the upper right corner of the Hertzsprung-Russell diagram, are objects of extraordinary volume but relatively modest mass. They have expanded in the late stages of their evolution to sizes that are genuinely difficult to conceptualize. Our Sun, the star at the center of our solar system, is approximately 1.4 million kilometers in diameter. This already seems like a large number if you were to travel around the Sun's equator at the speed of a commercial aircraft. The journey would take approximately 220 years. But place the Sun next to a true red supergiant, and it becomes a marble beside a house. The largest known red supergiants have estimated radii more than 1,500 times that of the Sun. Their surface, if we could stand upon it, would be so far from their own core that the density of the material there is lower than the air at the edge of Earth's atmosphere, the boundary we conventionally define as the beginning of space. These stars are, in a meaningful sense, barely more substantial than a very large cloud. Walk through the outermost layers of the largest known stellar objects, and you would notice nothing. There would be no resistance. The material is that diffuse. This combination, enormous volume, relatively modest mass, produces something paradoxical. A star with a surface gravity so weak that it can barely hold itself together. The largest red supergiants pulsate irregularly over timescales of months to years, their outer layers expanding and contracting, driven by complex processes involving convection, radiation pressure, and the changing opacity of the stellar material. Their apparent brightness as seen from Earth varies measurably during these pulsations. The scale of these expansions and contractions is itself extraordinary. A red supergiant changing its radius from 1700 to 2000 solar radii is moving its outer layers at velocities comparable to those of spacecraft. These stars are approaching the end. They have exhausted their hydrogen, progressed through helium burning and beyond. The nuclear reactions in their interiors are working through the elements of the periodic table in sequence, approaching iron, approaching the end of the line on cosmological timescales. The explosion is imminent. On human timescales, it could happen tomorrow or in 100,000 years. We cannot predict it precisely. We only know that when it happens, the result will be briefly visible across intergalactic distances. A single star will outshine its entire galaxy for a few weeks, then fade. The remnant it leaves behind will glow for millennia. And then, eventually, even the nebula will disperse, and the stellar material will join the general interstellar medium, awaiting incorporation into the next generation of stars. Somewhere at the far edge of the solar system, there is a reservoir we have never seen. Its existence is inferred rather than observed, deduced from the behavior of objects that occasionally appear in the inner solar system after journeys of millions of years. Astronomers call it the Oort cloud. The solar system that we observe with planets and moons and asteroids and the Kuiper belt extends to perhaps 50 or 60 astronomical units from the Sun, 50 to 60 times the Earth-Sun distance. But the Oort cloud is thought to begin at around 2,000 astronomical units and to extend outward to perhaps 100,000 astronomical units, nearly halfway to the nearest star. Within this vast spherical shell, numbering in the trillions, are icy objects left over from the formation of the solar system. Comets waiting. Some have been waiting for 4.5 billion years. The objects in the Oort cloud were not always there. They formed in the warmer inner solar system in the vicinity of the giant planets, during the chaotic early period when Jupiter, Saturn, Uranus, and Neptune were completing their own formation and migrating to their current positions. The gravitational influence of these giants scattered smaller icy bodies outward, some entirely out of the solar system, some into highly elongated orbits that took them deep into interstellar space and then brought them back, and some into the distant reservoir that became the Oort cloud. The process was violent and efficient. Billions of objects were ejected over millions of years. What we observe today as the outer Oort cloud is the residue of that formative chaos. Every few million years, the equilibrium of the Oort cloud is disturbed. A passing star, or the differential gravitational pull of the Milky Way galaxy itself, the tidal force that the galaxy exerts on the outer solar system, perturbs some of these distant objects, altering their orbits just enough to send them falling inward. The journey from the Oort cloud to the inner solar system takes millions of years. The object, initially cold and dark, barely distinguishable from the surrounding space, begins to heat as it approaches the sun. Ices on its surface begin to sublimate. Water ice, carbon dioxide ice, carbon monoxide ice, methane ice. The released gases carry dust particles with them. A coma begins to form, a fuzzy atmosphere surrounding the solid nucleus. The solar wind pushes the released material away from the sun, creating tails that always point away from the sun, regardless of the direction of travel. What arrives in the inner solar system is what we call a comet, a remnant of the solar system's birth, momentarily illuminated after an almost incomprehensibly long journey. Long-period comets, those with orbital periods of thousands or millions of years, are the most dramatic. They appear suddenly in the sky, brighten over weeks or months, then fade and recede. Some of them make only a single pass through the inner solar system. Their orbits are so elongated that they may not return for tens of millions of years, if ever. Others are captured into shorter orbits by gravitational interactions with the giant planets and become periodic visitors. Halley's Comet, returning every 75 years, is the most famous of these. The composition of comets has been a subject of intense study for decades. They are, in a sense, time capsules, objects that have been preserved at extremely low temperatures in the outer solar system since the formation of the solar system itself. The material they contain, the ices, the organic compounds, the silicate dust, provides direct samples of the materials from which the planets were built. Analysis of comets has revealed the presence of amino acids, the building blocks of proteins, and of complex organic molecules that were once thought to be exclusively biological in origin. The suggestion that comets may have delivered some of these materials to the early Earth, possibly contributing to the origin of life, is a hypothesis that continues to be investigated. We do not know if life began with ingredients delivered from space, but we do not know that it didn't. The inner Oort cloud, sometimes called the Hills cloud, after the astronomer who first predicted it, is more tightly bound gravitationally to the Sun and less susceptible to perturbation. It is thought to contain objects scattered by the giant planets during the early solar system that did not receive quite enough energy to reach the outer Oort cloud. Observational evidence for this region is indirect. The orbital characteristics of some known trans-Neptunian objects suggest that they have been influenced by material in the inner cloud. But direct detection remains beyond our current capabilities. The objects are simply too small and too far away and too dark to see with present technology. What we can see occasionally is the result of perturbations to this region. If a star passes within a few light years of the Sun, as stars occasionally do over the course of billions of years, the gravitational disruption can send objects from the Hills cloud inward, producing a prolonged increase in the rate of cometary impacts on the inner planets. Some researchers have linked such events to mass extinctions in the fossil record. The evidence is suggestive but not conclusive. The history of life on Earth has been shaped by many factors, and separating the influence of cosmic events from geological and atmospheric processes is genuinely difficult. What is clear is that the solar system does not exist in isolation. It moves through the galaxy, and the galaxy acts upon it slowly, persistently, and occasionally catastrophically. On the night sky, every star we see is in motion. This is not apparent to casual observation. The stars appear fixed, immovable, the very archetype of constancy. But appearances are deceiving. The stars we see are moving relative to each other and relative to us at velocities of tens or hundreds of kilometers per second. On timescales of tens of thousands of years, the familiar constellations will deform and eventually become unrecognizable. On timescales of millions of years, stars can move thousands of light years. On timescales of billions of years, individual stars have crossed the galaxy multiple times. In regions where stars are more densely packed than in our neighborhood, particularly in globular clusters, dense spherical collections of hundreds of thousands to millions of stars orbiting outside the main disk of the galaxy, the probability of close encounters between stars increases dramatically. In the most crowded cores of the densest globular clusters, the average distance between stars can be less than a light year. Stellar collisions and mergers, events of essentially zero probability in our vicinity, occur there at a rate of perhaps 1 per 10,000 years. That is still slow by human standards, but it is fast enough that the cumulative effect over billions of years has been significant. When two main sequence stars collide, the result depends on the relative masses and velocities of the participants. A slow, close encounter between two stars of similar mass may result in a merger, the two objects spiraling together under gravitational attraction, their material mixing and eventually settling into a single, more massive star. These merger products are called blue straggler stars. They appear bluer and younger than the surrounding stars in the cluster, because the merger has effectively rejuvenated them by providing new hydrogen fuel to an aging stellar core. They should not exist by the standard rules of stellar evolution. Their presence in globular clusters is direct observational evidence that stellar collisions occur. The merger of more exotic objects produces more exotic results. Two white dwarfs in a close binary system lose energy to gravitational wave emission, spiraling ever closer until they finally merge. If their combined mass exceeds the critical threshold, the result is a thermonuclear explosion, a type Be supernova, the same category of event used as a cosmological distance indicator. The universe, it turns out, uses stellar collisions as a calibration tool. The distance to the farthest observable galaxies was determined in part by the light of merging dead stars. The merger of two neutron stars is an event of extraordinary violence and extraordinary productivity. As the two objects spiral together, they emit gravitational waves, ripples in the fabric of space-time at an increasingly rapid rate, losing energy to radiation and accelerating their spiral. The final merger, lasting a fraction of a second, releases gravitational wave energy equivalent to several percent of the combined stellar mass. The gravitational wave signal from such an event sweeps rapidly upward in frequency. The event is simultaneously a gravitational wave source, a gamma-ray burst, a kilonova, and a heavy element factory. It is, by many measures, the most productive event in the universe. There are theoretical objects more exotic still. Consider the possibility of a neutron star orbiting inside a red giant. This is not a configuration that arises easily, but it is one that stellar evolution can produce, in a binary system where one star has already ended its life as a neutron star, and the companion has evolved into a large, diffuse giant. The orbital dynamics can, under some circumstances, cause the neutron star to spiral inward through the giant's envelope. What happens next is the subject of theoretical speculation and computer simulation. The neutron star, incredibly dense and compact, would not simply be absorbed. Its gravity would draw material from the surrounding giant's interior, possibly initiating nuclear reactions, altering the giant's energy output, modifying its appearance. The result, a star with a neutron star buried at its center, would be unlike anything we have directly observed. It would look from the outside much like an ordinary red supergiant, but its internal physics would be governed by the presence of that neutron core. These theoretical hybrid objects have been predicted to exist for decades. Identifying one in the real universe remains a challenge that future astronomical surveys may finally be able to address. The universe, considered at full scale, is a place of almost incomprehensible extremes. Temperatures ranging from nearly absolute zero to the Planck temperature. Densities ranging from the near-perfect vacuum of intergalactic space to the nuclear density of neutron star interiors. Distances so large that light requires billions of years to cross them. Timescales so short that events of cosmic significance unfold in microseconds. And all of it operates according to physical laws that can be written on a few sheets of paper. What is extraordinary is not that the universe is complicated. What is extraordinary is that it is comprehensible at all, that the same equations describing the behavior of gases in a laboratory also describe the dynamics of galaxy clusters, that the nuclear physics measured in accelerators on Earth also explains the energy output of distant quasars, that mathematics developed by human minds for its own internal logic turns out to be the language in which the universe is written. This coincidence, if it is a coincidence, has never been satisfactorily explained. It may never be, but it is perhaps the most remarkable thing about living in this particular universe. We began with temperature, with the measurable fact of heat and cold, and we end here at the edge of what measurement can reach, the point where our instruments run out, where our theories become uncertain, where the questions multiply faster than the answers. The universe is approximately 13.8 billion years old. Life on Earth has been present for perhaps 4 billion years. Civilization in any meaningful sense for perhaps 10,000. The instruments capable of detecting gravitational waves and merging neutron stars, and the expansion history of the universe, these have existed for decades at most. We are, cosmically speaking, very new here, and we are just beginning to look around. What we have found in that first tentative survey is astonishing. A universe of spinning neutron stars, colliding galaxies, erupting moons, evaporating comets, vanishing stars, expanding space, and a background glow from an event 14 billion years in the past. A universe that apparently began at a temperature without limit and has been cooling and structuring and complexifying ever since. A universe that produced among its billions of galaxies and trillions of stars at least one warm wet planet, circling a middling star in a spiral arm of a middling galaxy, upon which matter organized itself into structures capable of wondering about the universe that made them. That is where we are. Standing on a cooling ember of a long-ago explosion, looking outward with our limited instruments and our imperfect theories, and finding at every turn that the universe is larger and stranger and more orderly and more violent and more beautiful than we expected. The questions do not diminish as knowledge increases. They multiply. Each answer opens 10 new questions. The frontier does not recede, it expands. This is what it means to study the universe, not to arrive at final answers, but to push the boundary of the unknown a little further out, to sharpen the view through one more increment of precision, to find that what we thought was the edge is only another beginning. The sky above us is not a ceiling, it is a window, and beyond it, the universe waits, indifferent and magnificent, full of fires we have not yet named.